Hello everyone. Today we are going to discuss the chemistry of group 15 elements part 2. In the previous videos we have discussed the general properties of group 15 elements like ionization energy, electronegativity, the compounds of group 15 elements like hydrides and oxides. Today we are going to discuss the preparation and properties of dinitrogen, preparation and properties of NH3, oxides of nitrogen, preparation and properties of HNO3, allotropic forms of phosphorus and their reactions, some phosphorus compounds and their structures, and ultimately oxoacids of phosphorus and their acidity. Now let's go for the first topic, preparation and properties of dinitrogen. First of all, the laboratory preparation of dinitrogen. As you can see over here, then when we uh, react ammonium chloride aqueous solution with sodium nitrite aqueous solution, we obtain uh, dinitrogen as a major product along with the water and NaCl. Okay. Secondly, if we heat ammonium dichromate, then also we can get nitrogen as a major product. Thirdly, if we heat the azide compound of alkali metals like sodium azide, NaN3, if we heat NaN3, we can get sodium and dinitrogen as the major product. Now coming to the properties of nitrogen. What are the properties of nitrogen? First of all, nitrogen reacts with alkali metals to give their corresponding metal nitride. As you can see over here that lithium and magnesium are reacting with nitrogen and forming their corresponding nitride. Lithium is reacting with nitrogen forming lithium nitride. Magnesium is reacting with nitrogen forming magnesium nitride, Mg3N2. Secondly, nitrogen reacts with hydrogen and oxygen to give ammonia and nitric oxide. Here, as you can see, nitrogen is reacting with hydrogen in presence of heat, forming ammonia, and also nitrogen is reacting with oxygen, forming nitric oxide. The first process of ammonia production is mainly called Haber's process that we will discuss later on. Now, preparation properties of NH3. So as we have discussed already that the production of ammonia by Haber's process where nitrogen and hydrogen are combining together in the pressure range 200 atmosphere, temperature almost 450 degrees centigrade, and a catalyst is used in this process which is iron and molybdenum mixture. Then we can get ammonia as a major product, and this process is called Haber's process of ammonia production. So first of all, this process is an exothermic process. The process of ammonia production by Haber's process is an exothermic process. As we have discussed in class 11 that for an exothermic process, if we maintain the temperature of that reaction very low, then the reaction will occur in the forward direction, right? So here the temperature is almost in almost very low value, 450 degrees centigrade, and that's why the condition for good ammonia production is to maintain the low temperature, that is below 500 degrees centigrade. Here we have used 450 degrees centigrade temperature for the ammonia production. Now secondly, the pressure that we have to maintain throughout this reaction is high pressure. Okay, because high pressure, if we maintain high pressure, then reaction will try to decrease the pressure, and reaction will move in that direction where the pressure of the gas is less. As you can see over here that ammonia the pressure in the product side is less and pressure in the reactant side is more. So if we maintain the high pressure that is 200 atmosphere, then the reaction will be in the forward direction. Okay, so what are the conditions for good ammonia production? Low temperature, that is below 500 degrees centigrade, and high pressure. Moreover, here we have to use a catalyst that can catalyze this process, because the process of ammonia production is a comparatively slow process. So here we use iron molybdenum mixture as the catalyst. Now we are coming to the properties of ammonia. Ammonia, as we have learned or as we have done in the practical of class 11 and 12, class 11 mainly, that copper salt, it may be copper sulfate, it may be other salts of copper salt that contains copper 2 plus reacts with ammonia to form copper amine complex. This is the copper amine complex, CuNH3 whole 4 2 plus. This copper amine complex has the blue color, deep blue color. Okay, moreover, silver ion, like copper ion, silver ion also reacts with ammonia to form silveramine complex. Okay, now what are the oxides of nitrogen? This is a very important topic. Generally, the question comes in this way: what are the oxides of nitrogen? Mention their structures and the oxidation state of the central nitrogen atom. Okay, so here mainly we will discuss about the oxides of nitrogen, which are N2O, NO, NO2 and N2O4. As we have seen, as we are observing here, that N2O has a linear structure. Okay, NO has also a linear structure, NO2 has a bent structure, and N2O4 has this kind of structure. Okay, it's very important to observe one thing, that NO2 contains a lone electron, that means odd electron. As we can see over here, the nitrogen contains an odd electron, and that's why this NO2 can combine with another fragment of NO2 forming N2O4. Okay, so these are the structures of N2O, NO, NO2 and N2O4. Here you can see the oxidation state of nitrogen, central nitrogen atom, in these compounds. In N2O, central nitrogen atom has oxidation state +1. In NO, it is +2. In NO2, it is +4. In N2O4, it is +4. Now, the preparation process of this N2O, NO, NO2 and N2O4 I have mentioned here. N2O is prepared by heating ammonium nitrate. Okay, NO is prepared by treating sodium nitrite solution with ferrous sulfate solution in presence of H2SO4, and NO2 and N2O4 are prepared in the following processes, right? Now we are coming to the preparation and properties of HNO3. First of all, what is the laboratory preparation of HNO3? HNO3 is prepared in the laboratory by mixing potassium nitrate solution with concentrated H2SO4, and we have to heat the mixture, and in that case we can get nitric acid as a product. Okay, what is the industrial preparation of nitric acid? Nitric acid is mainly prepared industrially by Oswald process. This process contains the following steps. First of all, step 1. In step 1, ammonia is oxidized. In presence of platinum and rhodium catalyst, maintaining the pressure 9 bar and temperature 500 Kelvin, giving you nitric oxide and water. In the second step, the nitric oxide reacts with oxygen, or rather we can say nitric oxide is oxidized with gas, oxygen gas, maintaining where we have to maintain the temperature below 100 degrees centigrade, and we can get nitrogen dioxide. In the third step, the nitrogen dioxide produced in the second step absorbs water in presence of air, that means oxygen, forming the HNO3 as the major product. Now let's come to the reactions of HNO3. In the reactions of HNO3, the most important reaction is the oxidizing property or oxidizing nature of HNO3. HNO3 is a strong oxidizing agent. As you can see over here, that copper, that is a metal that reacts with HNO3 and forming the copper nitrate with the liberation of nitrogen dioxide and water. Okay, so here as we can easily observe that copper is being oxidized to copper nitrate, and and this HNO3 is being reduced to NO2. The oxidizing property of HNO3 is also shown in this second reaction, where carbon is reacting with HNO3 forming carbon dioxide, NO2 and water. Here carbon is being oxidized to carbon dioxide and HNO3 is being oxidized to NO2. Now let's come to the brown ring test, that is very important for the practical purposes of class 11 and class 12 as well. Okay, where we take a nitrate salt. This nitrate salt, we mix this nitrate salt with ferrous sulfate, freshly prepared ferrous sulfate, that is Fe2 plus, in presence of concentrated H2SO4 or concentrated HNO3 as an acid. Okay, in the first step, nitric oxide is produced with the liberation of iron 3 plus, where iron 2 plus is oxidized to iron 3 plus and NO3 minus is reduced to NO. The nitric oxide formed in the first step reacts again with the iron 2 plus salt uh, to form a complex compound, that is FeH2O whole 5 NO2 plus. This complex compound is responsible for the brown ring that is formed in the middle of the test tube during the test of nitrate, that is called the brown ring test. As you can see over here, that in this way the ring is formed in the test tube. Now, what are the allotropic forms of phosphorus and their reactions? There are mainly three kinds of allotropic forms of phosphorus are there. First of all, white phosphorus. This is the structure of white phosphorus. As you can see over here that the structure is a tetrahedral structure where 4 phosphorus atoms are connected with 4 covalent bonds, and the angle, this angle is almost is very less to the expected angle of tetrahedral structure. In tetrahedral structure, the angle is 109 degree 28 minute, but here the angle is very less than 109 degree, and due to this strain of angle, the white phosphorus is very much reactive, okay, in comparison to the other allotropic forms of phosphorus. So and it is secondly, it is very unstable due to angular strain. Thirdly, we can say that it is insoluble in water but soluble in carbon disulfide, and due to its reactive nature, we can say white phosphorus reacts with oxygen to give P4O10. Now let's come to the red phosphorus. Red phosphorus is another allotropic forms of phosphorus which is basically obtained by heating white phosphorus. This is the structure of red phosphorus. Here the tetrahedral units, the P4 tetrahedral units are connected by phosphorus single covalent bond, right? So this form of phosphorus, that is red phosphorus, is insoluble in both water and carbon dioxide. Now the most unreactive or very less reactive forms of phosphorus is black phosphorus, that is obtained basically by heating red phosphorus at high temperature. uh, Red phosphorus is insoluble in both water and carbon disulfide, and it doesn't react in air. If we heat the black phosphorus in air, it will be sublimed to the gas form. It doesn't burn at all up to 670 Kelvin. That proves that black phosphorus is very much unreactive in comparison to the other allotropic forms of phosphorus. Now let's come to the some phosphorus compounds and their structures. First of all, phosphine. Phosphine is generally prepared by reacting white phosphorus with NaOH solution. Here we can get PH3 phosphine with the liberation of sodium hypophosphite NaH2PO2. Secondly, phosphine has basic property like NH3. PH3 has a basic property like NH3 because phosphorus of PH3 contains lone pair of electrons that can easily take a proton from any acids like HBr, as we have shown here. That PH3 is accepting one hydrogen or proton from HBr, forming phosphonium bromide salt pH4 plus and Br minus. Now we are coming to the preparation of PCl3 and PCl5, that are different that are another compounds of phosphorus. PCl3, phosphorus trichloride, is basically obtained by reacting white phosphorus with thionyl chloride SOCl2, forming the PCl3 with the liberation of sulfur dioxide. Now PCl5, phosphorus pentachloride, is obtained uh, by reacting white phosphorus with sulfonyl chloride SO2Cl2, forming PCl5. uh, the important reactions of PCl3 and PCl5 are basically the hydrolysis reactions. So PCl3 is reacting with water, forming H3PO3 with the liberation of HCl, and PCl5 is reacting with water, forming POCl3 or H3PO4. If we use excess water, then we will get H3PO4 phosphoric acid as major product, and if we use calculated amount of water, then we can get this POCl3 with the liberation of HCl. Now this is the structure of phosphine. As you can see that it is a pyramidal structure where phosphorus is bonded with 3 hydrogen in a pyramidal fashion, and these are the structures of PCl3 and PCl5, where PCl3 has pyramidal structure like PH3 and containing a lone pair on phosphorus atom, and PCl5 has trigonal bipyramidal structures. The structures of these compounds you can derive from by the application of BACPR theory also. Now coming to the last topic of this chapter, oxoacids of phosphorus and their acidity. There are mainly 3 oxoacids of phosphorus we can get. First of all, H3PO4 phosphoric acid, H3PO3 phosphorus acid, and H3PO2 hypophosphorus acid. As you can see over here that these are the oxoacids of phosphorus: H3PO4, H3PO3 and H3PO2. Now here oxygen atom of phosphorus is connected with oxygen atom is connected with phosphorus by double bond in each of these structures. Oxygen, being electronegative in nature, will pull the electron cloud towards itself and causes an electron deficiency in this phosphorus atom, as I have shown. in these figures, and eventually the electron deficiency is also created on the oxygen atom of OH bond. Now for this reason, hydrogen atom of OH will leave the compound and compensates the electron deficiency of oxygen atom of OH bond. Now as we can see over here, in H3PO2 there is only one OH bond or one OH group, and that's why it is experiencing the entire pulling effect, that means 100% pulling effect of P double bond O bond, and that's why hydrogen atom is easily eliminated and showing maximum acidity. In case of H3PO3, where there are two OH groups are there, so each OH group is getting 50% of this pooling effect of P double bond O bond, and hence the chance of elimination of this hydrogen from this compound is little less than H3PO2. In case of H3PO4, there are three OH group, so each OH group over here is getting almost 33% of this pooling effect of this P double bond O bond, and hence the chance of elimination of hydrogen is very less. Rather we can say it here in this compound of H3PO4 there is least chance for this hydrogen to be eliminated from this compound. So the acidity order is going to be H3PO2 is greater than H3PO3 is greater than H3PO4. So these are the important concepts of group 15 elements. Hope you have understood all the topics. Thank you for watching this video.